It all began with radiocarbon dating. And to do it, you just measure the carbon-14 to carbon-12 ratio in a sample. Now, because it's a radioactive isotope, the people who started this and who developed radiocarbon applications speak of activity. They think of, so that you find this symbol in the carbon-14 literature, the same way we use an isotope ratio in stable isotopes, they refer to activity. But that activity is in fact just a carbon isotope ratio, if you think about it, in the ways that are familiar to us. So imagine you go to Tutankhamun's tomb and you pull out a piece of wood and you measure an activity and you want to know how old the tomb is. Well, you know that there's a radioactive decay law with a half-life, and so you can measure the carbon-14 abundance in modern carbon right now, and you can assume that's where Tutankhamun's piece of wood started, and you can measure how much carbon-14 is in that piece of wood now, and then using the radioactive decay equation, you can calculate the life. So you can essentially assume in that way that the amount of carbon-14 available to the biosphere over time has been constant, and you can then calculate an age based on that assumption. Or you can get a little bit fancier, which is how this all began, by taking artifacts for which the age is really known and measuring the current activity. And in fact, the first application of that sort of thinking was to estimate the half-life of carbon-14. And that was done by Willard Libby immediately after the Second World War. And he estimated, by using this technique in which he dated known artifacts that were English land deeds that were ancient and had a particular date, Tutankhamun's tomb and various Egyptian artifacts for which historical dates had at least been estimated, he came up with a half-life of 5,568 years, which we refer to as the Libby half-life. It's approximately correct, but not exactly. It's interesting that even though I just had to say it's approximately correct, we still use the Libby half-life to calculate radiocarbon age expressed in radiocarbon years, which you can be warned are different than real years. And they're different because the idea that the starting abundance of carbon-14 has always been the same is incorrect for a bunch of reasons. One is that since the dawn of the Industrial Revolution, we've been burning fossil fuels. The fossil fuels are millions of years old. There is no carbon-14 in them at all. We are puking into the atmosphere what people call dead carbon. There's no carbon-14 in it, and we've done so much of it that we've diluted the atmosphere with fossil fuel CO2, and that has pulled down over time the abundance of carbon-14 in the atmosphere. This is known as the Seuss effect. It was first recognized by Rainer Seuss. The other thing is that the rate of production of carbon-14, which comes from the impact of cosmic rays on the upper atmosphere, has varied over time because the geomagnetic field has varied. Now you're going to say, if you're thinking physically, look, the geomagnetic field is not going to affect a neutron. The neutron that creates carbon-14, according to the reaction shown here is a secondary product from cosmic rays that do have charge and are steered by the geomagnetic field. We've also, of course, polluted the atmosphere with physiogenic carbon-14 that has been created by atmospheric testing of nuclear weapons. And also, the atmosphere, there's this marvelous guy who was one of the other teachers in this course that I taught in 1982. Wally Broker, a chemical oceanographer at Columbia University, says, the atmosphere is the ocean's slave. That's his way of expressing the relationship between carbon dioxide in the atmosphere and carbon dioxide in the ocean. There's 59 times more carbon dissolved in the ocean than there is in the atmosphere. So over time, we've had surging flows of CO2 from the ocean into the atmosphere and vice versa. And the carbon dioxide in the ocean has been stirred around in the ocean for thousands of years. It's depleted in carbon-14 simply by the passage of time. So if there's an interval of Earth history in which the ocean has been upwelling strongly and putting lots of its CO2 back into the atmosphere, that pulls down the abundance of carbon-14 in the atmosphere and has an effect on the starting point for carbon-14 in the terrestrial biota. So that's another factor that's been affecting the starting point. So you've got multiple causes of inconstancy in the starting point when you're looking at something and trying to compute a radiocarbon age. The solution to that set of multiple problems has been slowly but surely to do the same sort of thing Libby attempted at the beginning, a calibration, but to do it now on a vastly expanded scale with far greater precision. And it's, of course, one of these things where you have to have a huge accumulation of data to eliminate errors and to be sure that you're doing the best possible job. And there's an international calibration body that issues reports every once in a while. The most recent is this IntCal13. These typically appear in the journal Radiocarbon, which is highly specialized, but a wonderful source of information. And you see the cast of characters. Paula Reimer has been leading this exercise for a very long time. There are a lot of other household words there, household names there. Who should I point out? Peter Grutz has been one of the heroes of this business for a long time. Johannes van der Plicht is another. There are people here who have invested huge amounts of time in this process. And they have a downloadable program that is, by now, it's evolved to the point it's idiot-proof. You can put in a radiocarbon age, and it tells you what it really means with marvelous clarity. It's a very, very good system. So here's the way the calibration now looks. On the vertical axis, we have the measured radiocarbon age from that very rudimentary equation that was on sort of the first slide. You calculate, and an analytical laboratory will report to you a radiocarbon age. That corresponds to an actual calendar age in calendar years rather than radiocarbon years, as shown here. And you can see that in general, throughout the applicable range, at 50,000 years, you're almost 10 half-lives back, which means there's practically no carbon-14. This is roughly the deadline, what people in the analytical business call the deadline of carbon-14. You're not going to get much farther than 50,000 years, no matter how excellent your facilities and techniques are. But you find that a measured radiocarbon age of 25,000 years corresponds to an actual age of nearly 30,000 years, which means, if you think about it, backwards in time, there was more carbon-14 in the atmosphere than there is now. There were higher abundances. Another problem that will occur to you in particular is that when you look at carbon-14 in any given sample, it's going to have been fractionated just as carbon-13 is. In fact, since it differs from the major isotope by 2 mass units instead of 1, it's fractionated twice as much, which actually is a way of making a sample look older because it has less carbon-14 in it because of that fractionation. To get away from that, the analysts right away report to you not the actual amount of carbon-14 that was in the sample, but instead how much carbon-14 there would be in it if the delta 13C value was minus 25. It's a very useful way of eliminating the isotopic fractionation effect. If you think about it, they could normalize it to anything they wanted. They could normalize it to 0, they could normalize it to minus 50. Minus 25 they just chose as a typical organic delta value, and they normalized the carbon-14 abundances to that same level. In other words, if the sample had a real delta value of delta 13C value of minus 25, they just report to you the raw carbon-14 abundance. But if it was minus 50, they take that into account and they report to you an elevated carbon-14 abundance by the amount required, to account for the fractionation. Let me just put it that way. The correction factor is this one right here. So you measure a raw carbon-14 abundance, and you correct it by this factor, which is shown here. It means if it's minus 25, as I said a minute ago, you just multiply by 1. If it's minus 50, you multiply by this number to increase the amount of carbon-14. If it were 0, if it were a carbonate shell, you'd multiply by that factor to decrease it and bring it down to what it would be at minus 25. Is that okay? Any question? Okay. There's a last point in that we have to define this value modern. That the radiocarbon age, way back at slide number 1, was based on fraction modern. And the question is, okay, every laboratory has to have the same definition of modern. And the arbitrary point chosen for modern was 1950. And so the idea was to know what the abundance of carbon-14 in the atmosphere would have been in 1950 if there hadn't been an industrial revolution. And there hadn't already been the Seuss effect at work for about a century. So this is not anything that you could measure. It's a concept. And people made the best estimate of what the abundance of carbon-14 in the atmosphere in 1950 would have been if it hadn't been for the Industrial Revolution. And they defined then, they had a standard oxalic acid isolated from molasses. Terry, do you know why oxalic acid was chosen it was an available National Bureau standard that they set, and I can't remember the ultimate reason why, but anyway, it was defined as 95% of the activity of carbon-14 in that oxalic acid standard in 1950 is going to be defined as modern. So now, let's say in 2016, we measure the oxalic acid standard, and that tells us what the abundance of carbon-14 in that standard is now. And so we use the actual physical half-life, which we now know is 5,730 years, not 5,568 years. And we use that actual physical half-life to correct the measured activity now back to what it would have been in 1950. And that provides us with our definition for any given measurement of modern, the abundance of carbon-14 in 1950. And we use that normalized oxalic acid number and compare it to our normalized sample number, and we get the now modern, or the now up-to-date and currently defined radiocarbon age. Okay? Don't be put off by all the jargon. You've heard it once. And you can look, anybody else starts talking to you about it, you can nod knowingly.